Hello and welcome back to Calculus 1 section 3.9 on derivatives of exponential and logarithmic functions. Ready? Got your popcorn and everything? Good. And your energy drinks. So I understand. So we are going to talk about exponential functions. We already know the derivative of exponential function. We're just going to supercharge it a little bit and then switch to logs, which is the topic for tonight. So, we're going to spend about 90% talking about logs tonight. So first off, let's take care of the exponential functions. So the derivative of e to the x is just e to the x. There is an easy proof using the limit definition. If you, want to work it out, but we don't have to. The formula that you were asked to memorize before you learned chain rule was derivative of e to the ax is a e to the ax. So that's the formula you were asked to memorize, and now that you know the chain rule, you know how to actually obtain this one. Now the formula for tonight, the star of the exponential part, is the derivative of e to any function of f, any function f there. So e to the sine x, e to the x squared plus 3, e to the square root of x minus 1, e to the x, and so on. So any function, not just a linear function as before. Now we are allowed to have any function in there. And then by chain rule, it's simply e to the f of x times f prime of x. Now, this is going to be the exponential star, all right? This is the function that we all want to know, because that one is going to cover 99% of your problems. Nice one. Thank you. And if you consider exponential functions, you also know that your base e doesn't need to be e. Could be 2 to the sine x, could be 4 to the tangent x, and so on. So the general form, which you are not going to see pretty much at all, is given by the derivative of b to a function. So this would be the boss equation, You would think that this b stands for a base. It stands for boss. So this would be the boss equation because you can have any base, not just e, any base and then any function. And that derivative is going to be b to the f of x times f prime of x, just like up there, and then times ln of b. Now, I'm not going to make a big deal out of this formula. It doesn't get a cloud. It gets the red box. It's the general form. But as I said, in nature, you generally see functions that are e. You want to talk electrical engineering, charging and discharging battery, charging or discharging capacitor, it's going to be E. You want to talk about population, you want to talk about decay, you want to talk about technically everything is just E. Are we going to have other bases? Yes, you're going to have a base of 10. If you want to talk about waves, you want to talk about earthquake, you want to talk about light waves, I got the theme shirt today because I knew I was going to mention it. So if you want to talk about pH values in chemistry, you're going to use base 10. If you want to talk about, did I say earthquakes, Richter scale? So base 10 is out there. but it's insignificant in comparison to how many functions are driven by e to the sum function. So I would say that 99% of your problems are going to fall in the red formula up there, and actually 1% is going to be purple. But still, purple is the most general problem you can get. I mean, most general formula you can get. So now, using the purple formula, find the derivative of 6 to the cosine x. Do we all see the Control-C, Control-V part? Right? Control-C, Control-V, get the derivative, put ln of 6 and be done. So if I put a problem similar to this one on a test, I'm not just expecting the answer, I also expect to write thank you next to it. Yeah, it's like a small thank you. So, Control-C, Control-V, right, because that's the same. So, Control-C, Control-V, you begin there. Then the derivative of the exponent, derivative of cosine is? Negative. Oh, you guys should have a choir going. And ln. Oh, now quiet, everyone. It's like, no, I'm not going quiet. ln 6. Good. That's it. Move on with our life. We're done with exponential functions. There's nothing else. I'm sorry. This is it. I hope you're not disappointed. But that's it. That's your exponential function. So you learn this one formula.
Why is it times ln 6? I thought anything with ln was like a fraction. Should that be 1 over?
No, that's in the answer, not in the... We're not taking the derivative. Now we're going to do the logarithmic. Right?
What type are we talking about?
Pretty good. That's a pretty good draw. I think it's mahogany, maybe.
Mahogany.
No, it's cherry wood. It's definitely cherry wood.
Logs. Okay, there's no apostrophe, you're right. It's just... Alright. Logs.
Was that friendly harvested?
No.
It's a free-roll tree.
Wow. You tree killer.
Friendly harvested. Like the other, you know, I went to that wedding, right? Someone at one point asked, "Are those blood diamonds?" Of course, they're cheaper. Anyway.
I always loved the color.
All right, so let's go and talk about logs. Before talking about logs, let's just go back in time. Have some serious questions. 2 plus 3 is? Failed. And now we can undo this operation by using the, right, we can retrieve 2 and 3 by subtracting, right? Now, how about 2 times 3? 6. And then 6 divided by 3 is 2, and 6 divided by 2 is 3. Right, so we got this. Now, what is multiplication, right? Multiplication was fast addition. What is the meaning of 2 times 3? It means 2 plus 2 is 4 plus 2 is 6. But instead of adding 3 2's, we say 2 times 3 is 6. We memorize those. So multiplication is fast repeated addition. Great. Now, how about 2 cubed? 8. Good. And how much is cube root of 8? 2. how do we recover 3? How do we recover 3? Logs. Log of base 2 of 8 is 3. So now you have some kind of map in math, right? Do we all see where the logs belong? It's a mathematical operation that you discriminate against because you're awful people. You don't discriminate against addition, subtraction, right, multiplication, because they have cute symbols. But now log has letters, and all of a sudden, ooh, I don't want to, involve letters. So, right? Look at that.
3 letters too.
I know, makes it worse.
I can't read.
It shows. All right, so when you are looking at this roadmap, you see that there is operation that will undo addition. There is also operation that will undo multiplication. And there are 2 different operations that would undo exponents. So logs are not functions. They are calculation. You toss in 2 and an 8 and a log, in a bowl, you toss it a little bit around, and boom, 3 comes up, right? The same thing like you toss in 2 and a 3 and 5 comes up, right? If you put the plus. If you put 2 and a 3 and a times, 6 pops up. So the idea is that with logs, right, you will be able to undo the exponents. Now that gives us the most important conversion factor between the world of exponential and the world of logs. Again, we're talking arithmetic over here, no functions. Do you see any variables? No variables, no functions, right? So we are getting a conversion which says that a raised to the b equals c converts into log of base a of c will give me answer of b. And now you can, in your mind's eye, put 2, 3, and 8 into these and verify that they are in the right spot. So now that we understand that logs are nothing else other than a basic mathematical operation, just like all the other ones are, now that they are dear to us, like all others are, we can start involving variables. So how do you make a function a linear function? Well, you replace 2 or a 3 with x and you create a linear function x plus 3. How do you create another type of linear function? You replace 3 with x so you get 2x. That's also linear, right? So you can create all of these functions. Now, if you put in x for 3, you get 2 to the x becomes exponential function. Finally, if in a log you replace you replace 8 with x, you get what we call logarithmic function. And you study logarithmic functions in your pre-calculus course. Some of you was algebra 2, whatever it was. And for these particular functions, we have all of the goodies that we have for any function. We have domain, and range, and x-intercept, y-intercept, the inverse, and the whole spiel of things, right? Asymptotes. So now let's take a look at the basic specs of a log function. So log function would graph like this, going through number 1. And it has a horizontal asymptote on the y-axis, which is x equals 0, horizontal asymptote. So the specs for the log function are domain 0 to infinity, not including 0, because there is a vertical asymptote there. Range, all real numbers from negative infinity to positive infinity. It goes all the way down and all the way up in terms of y values. The x-intercept is at 1, 0, as you can see. The y-intercept is none, because there are no y-intercepts. You have a vertical asymptote. The vertical asymptote at x equals 0, which is y-axis. Horizontal asymptote is none. So these are the basic specs. You can also see that it does not have min and max. You can also see it's always increasing. There are other features that we are going to talk about in chapter 4, but right now we are basically repeating what you guys should know from your pre-calculus course with a chapter on exponential and logarithmic functions. So these are the basic specs of a log function. Let's put this in the green box. There we go. And now it's time to write certain facts here. So the log of base e of a number, well, let's just put x, is written as ln of x. So this is a natural log. This is the lazy notation. There is nothing, these two things are the same, right? If the base is e, we write it ln. It's just literally two letters shorter to write. That's all it is. It's just 2 letters shorter to write. You have this featured on your calculator on the button ln. The other one is log base 10 of x is just written as log x. So if you see no base, the base is 10, featured on your calculator as log. So when you take a look at your calculators, standard TI 8384, the ones that you can install on your phone if you have the right phone. There is the LOG button and there is the LN button, right? So those two are featured. Now, the more advanced the calculator is, the less log buttons it has, all right? So you have those, what they call scientific calculators, which would actually have log AB, which means that you can specify base and the number to calculate. Those are regarded as the new calculators. Then you have the next level, which are these calculators that have just 2 bases, E and LOG, which is the useful ones. And then the top tier is the one that either has LN or LOG, but it doesn't have both. That's the top. That's the top. So you can put that in that meme. You know the meme with the brain was so small and then lit up. And, yeah. So you can put that one. If anyone wants to bother with that, you can do it there. Yeah, post on the Discord, obviously. So why don't we need all of these? Because there is a formula that is called the change of base formula that you can convert. And that's why calculators don't need all of the bases. So change of base formula goes like this. Log of any base of any number is either ln of b over ln of a or log of b over log of a. So you are just going to use log or ln all the time. And this is the reason why you only need one. You don't need two of them. But TI, Texas Instruments, they're really nice people, so they include two. And I told you, right, that most of the stuff is just going to be done with ln, and then you will have few excursions into log when base is 10, primarily for waves and pH and chemistry and so on. Cool. Formulas that you really need to know. Ready? Number one, ln of x plus y, no, lies, x times y, is equal to ln of x plus ln of y. The product in the argument breaks as a sum of logs. Whether you're going to use ln or log base a, I don't care. You can use any of them. It's all the same, it's logs. Number two, ln of x over y is ln of x, come on, common sense, minus ln y. And the third formula that y'all must know is ln of x to the p is p ln x. I'm going to put this obviously on a cloud. It's not calculus stuff, but you can't do calculus if you don't know this. Right? So I'll give you some time to stare at these. Maybe put on a little index card next to yours, because we are going to use a lot of this. I need you to really know these formulas, and you'll see why. So start this and make sure. Right. So if chapter 3 is going to have something that is a God tier, that's this. And you'll see why. Not talking about gold, not platinum, God tier. That one. Cool. I have these other formulas that I call cute formulas. They're there just to, help us in some calculations. So log base a of a is 1, which means that the ln of e is 1, because we know that ln is a log base e, so ee, right? It's 1. And another cute formula, log of any base of 1 is always 0. Which makes sense if you convert, right? You will have a to the 0 equals 1. So we know when you raise a number to 0, you get 1. So I am going to lightly box these, because they show up in calculation, and then when you miss this kind of stuff, it's just embarrassing. It's not something that you lose points on. It just prompts me to write a noob next to it. As some of you would know by now, right? So how much is log 7 of 7? How much is log 7 of 1? 0. Beautiful. Those are the ones that we need. Good.
Promptly forget that.
That's okay. 4-letter word will fix it. Or should I add extra O's for this one? I don't know. Okay, cool. So now it's time to take a look at the derivatives of logarithmic functions. So we are starting with the one that you already know. The derivative of ln of x is 1 over x. So this is what you all waited for, right? The ln x is 1 over x. Perfect. So now, the next is the 1, okay? The derivative of ln of f of x. So guys, this is going to be ln of sine x, ln of x squared plus 1, ln of square root of 1 over x, right? Depends on how annoying you want to make it, right? So ln of f of x. And this is by far my favorite. It's f prime divided by f. This f over here, okay? So Control C, Control V. Max can also do something, I hope, similar, right? That they advance enough? Yeah, okay, good. And then you just take the derivative of whatever you have in denominator and put it up there, and you're done. So let's put this on a cloud. Really important stuff. All right, examples. Let's start with the exam question from last year. Calculus 1, exam 2. Question 8 or 9 or 10 or whatever it was. The derivative of ln of cosine x. Copy and paste from the test. I think it was like 4 points, or maybe 5, I don't know. 4. Looking at the formula, when you are taking derivative of ln, you put the division line, Control C, Control V on the denominator, and put the derivative on top, which is and negative tangent x as the answer. That's it. So there's your 4 or 5, I think it was 4 points, question on exam 2 from last year. Cool, right? Here's an interesting question. Derivative of ln of 6x. What's the answer? 1 over x. Dun dun. So you copy 6x in denominator, the derivative of this is 6 on top, and you get 1 over x. Oh! It's like that 6 was never there. How come? Well, it's math, so it's not magic. How come that the derivative of ln ax is just 1 over x, and this a, remember how a always pops out. It pops out for trig, it pops out for ease, and now for ln it's just poof, gone.
X plus ln 6.
Boss. Yes. This over here, using the God-tier equations, remember? Right? This over here breaks down into ln a plus ln x. What is a? Constant. So what is ln a? Constant. And what's the derivative of the constant? Potato. Good. Right? So now you know ln a is constant. And that's why. So those formulas, right? It's a number 1 up there. When your 6 was x and x was y, right? You get ln a plus ln x. ln a, the derivative of ln a is 1. So you can do that way as well. Wow, these logs are useful, huh? Cool. Let's do one more example. So we did what? We did 2 examples so far. Let's do another example just because we can, no coughing. So the derivative of ln of, what should I put here? Something cute. square root of 3x minus 1? Yeah, why not? Everyone is okay. No need to panic. Are you ready?
No, thank you. Missing the lesson of the light. All right. Whoa. Oh,
Alright, we have the boss move. I love it. That's okay. You need to practice. I mean, we just learned the derivatives, so it's okay. Alright. So this problem can be done the brute force way. Meaning, Chuck Norris shows up and you immediately put the square root in denominator, right? And then its derivative on top, which is over 2 square roots, and then times 3. And then you pretty much give up because it's a lot of work. But you have this over 1. So now 1 times 3 is 3, divided by 2. And then you have 3x minus 1 because square root times square root loses the root. That's a lot of work, right? Ready? So we have the square root of 3x minus 1. Isn't that square root a half exponent? Yeah, by the P rule, kick that outside, and you have ln of 3x minus 1. Right? So now you kick 1/2 outside. The derivative of 3x minus 1, right, I mean of ln 3x minus 1, you put 3x minus 1 on the bottom, its derivative on top, you're done. Welcome to logs. Which formula did I use? I used number 3 over here. That exponent of 1/2 is actually the square root. Alright, cool. So, yeah, that's the derivatives of the log functions, right? When you have this. You have a derivative of a log function. You just put the argument in denominator, take the derivative on top, and then if you need to simplify. Now, if you can use the log rules, woohoo, right? Because you can make it much easier and you can eliminate chain rule. You can eliminate product rule. You can eliminate quotient rule. It's really powerful stuff if you have logs around. All right, so that's exponential and logs. Let's see what else we can work out. The derivative of 3x squared minus, so let's say x squared plus 1 raised to the 6th power times cosine to the 4th x divided by the cube root of x squared plus 6x minus 2. That should be good enough. What? No, it's just a derivative. This is called flexing in mathematics. Like you go like, but it's all just numbers. Well, there are some numbers and some letters. So. Cool. Okay, let's analyze this. So what do we have here on a pile? Everything, right? I kind of dropped E, but so we have a quotient rule, right? No, yeah. So we have a quotient rule. And then when you have to do the derivative of the numerator as a product rule, and then each individual term is a chain rule by itself. Lock the doors. No one leaves. All right, now I'm going to sound like Morpheus. I'm not trying to, but I am. what if I told you that you can take the derivative of this particular function mentally without writing anything down and present the answer in a factored form ready for chapter 4? Also, every derivative we did so far in class falls in the same bag. Meaning, take everything else you learned, throw it away in chapter 3, and just look at every single problem up to tonight and just say the derivative without writing anything down, without working anything out, right? Without knowing any of the product rule or the quotient rule or anything like that. Wouldn't that be cool? It's not a prank, it's not a trap, it's the reality. It's happening. Which is why I'm always excited when 3.9 comes around. It's like, I get to talk about this. And all of you non-believers will be proven wrong. And you will feel terrible that you didn't believe in the power of law.
Scroll to the picture. Gotta get back to the picture.
Gotta back to the picture. So, what I am offering, guys, is not a fiction. I am serious when I say you're going to look at this thing like this, and you're going to say, well, that's easy. Just copy and paste the answer times, open parenthesis, and then you're just going to go and say, 12x divided by x squared plus 1 plus the 4 minus 4 tangent x minus 2x plus 6 divided by 3 quantity x squared plus 6x minus 2. Close parenthesis again. That's the derivative. In factored form. You just look at it and you instantly know. No need to write anything down. Now, if you need to do calculations for chapter 4, obviously write it down because you have to say equals 0 and then continue working on it. So let's learn the most powerful differentiation technique in the galaxy. It's called logarithmic differentiation. We're going to start slow and then, go there and just write the answer to anything like this. Which means the next time someone says, what do you know? Ask them to spell the word differentiation first, right? Then to spell the word logarithmic, then put them in the right order and then work out this problem. By that time, they're probably never going to talk to you again, which is just a plus. Let's go. So we are going to equals to question mark. We'll come back, right? Leave that there. Logarithmic differentiation. There we go. Logarithmic differentiation. Wow, this stuff is cool and powerful. Let's do a simple example. Say you are interested in the derivative of cube root of x plus 1 times, let's say, sine x divided by 3x plus 4 squared. Simple example. What you do is you set, leave some space, this function to y. This is mathematics behind it. Obviously, doing the problem mentally is a pattern. This is mathematics behind it to prove that, it works. And you ln both sides. Then you will use those formulas 1, 2, 3 that I told you the God tier, right? You're going to use those formulas to break the right-hand side into the logs, and all of the exponents also our arguments have to be in front. So we go ln y is equal to 1/3 ln of x plus 1 plus ln of sine x minus 2 ln of 3x plus 4. I used those formulas to come up with this expansion of logs. ln of xy is ln of x plus ln of y. All of these that are multiplied on top break down as addition, so you see a plus in between the cube term and the sign. If something is in denominator, like this y is in denominator, over there will be subtracted. So ln x minus ln y, you see that that 3x plus 4 squared term was in the denominator, so now it's minus exponent of 2, exponent of cube root, which is 1/3, is taken care of by the third rule, which is the exponent p, which gets dropped in front of ln. So now I need you to stare at the formulas and make sure that you can decompose this quickly. It's good to write the formulas. The more you copy these formulas, the better they'll stick in your head. It's okay to copy 1, 2, 3 in the margin of the problem. The more you copy them, the faster you memorize. We'll introduce you to some of the Eastern European education. The homework. Write these formulas 50 times. Comment next time. Oh, I forgot. Great. 100 times tomorrow. You're going to forget tomorrow. It's 200. Next time it's exponential growth. Because they're teaching you exponential growth. 50, 100, 200, 400. So you really don't want to miss it the first
So
time.
you just copy once and copy and paste?
No, it's done on paper. It's analog. You talk about the digital. It's Eastern Europe. The tablets are made out of stone. You got a chisel. All right. Yeah, that's why we're ripped. It's heavy stuff. We're not over here. Carry that stuff, Jim. All right. So, step number 1 is always to decompose. So you ln both sides, that's the red one, and then you decompose the complicated side into this. And aren't these all simple derivatives now? So when I hit both sides now with the derivative in respect to x, what happens on the left-hand side? What's the derivative of ln of y? It's 1 over y. Okay, I heard that. dy dx. That's your implicit differentiation. You took the derivative of y in respect to x. You have to follow with the chain. Now, the right-hand side has no chains because that's all. So what do we have? We have 1/3, copy the function downstairs, put the derivative up. Plus, copy the function downstairs, put the derivative up. Minus 2 times, copy the function downstairs, put the derivative up. Move y to the right-hand side, so you have your dy dx, which is derivative is equal to y times 1 over 3x plus 1 plus cotangent x minus 6 over 3x plus 4, and then just copy original problem into y and you're done. Original problem was this mess here. So copy the original problem. And now 1 over 3x plus 1 plus cotangent x minus 6 over 3x plus 4. And there you go. How many product rules did we do? 0. How many chain rules? 0. How many quotients? 0. Did you have them all? You had them all. We didn't do any of them. Welcome to logarithmic differentiation. Okay, let's do something from the past. How about the derivative of x squared times sine x? Remember how you use the product rule for this? Right? So y equals, leave some space, x squared sine x, ln both sides. And now you have your ln y is equal to 2 ln x plus ln sine x, right? Are we all bueno with this? Look at those formulas on the side. If you're confused, look at the formulas. Look what we're doing. So multiplication is broken into 2 ln's with the addition. And then the square on x goes in front using that formula number 3, the p, right? P is equal to 2. It jumps in front of ln. So now we differentiate the entire expression here. On the left-hand side, you have 1 over y dy dx. That's the basic of the implicit differentiation. You took the derivative of y in respect to x, so yeah. On the right-hand side, hold on, it's supposed to be like, there we go. On the right-hand side, you have the derivative of ln x, which is 1 over x, so 2 over x. Plus, you put the sine in the denominator and its derivative in the numerator. So now dy dx is equal to y times 2 over x plus cotangent x. And the y was x squared sine x. Dy dx is equal to x squared sine x times 2 over x plus cotangent x. Now, let's say you want to simplify this further, which you can. When you multiply x squared and x will cancel, so you get 2x sine x plus cotangent is cosine over sine, so sine will cancel, so you just have x squared times cosine x. There you go. Now he will say the product rule is much easier. Yeah, but you don't use the sledgehammer to put the picture on the wall, right? You can, as you can see, but there is no need. Now, what is the secret of that pattern that allows you to take derivatives of anything mentally? Well, first off, you see how in every problem the y pops out, right? Y is the original problem. So when I took the derivative mentally of that big problem when I posed it the first time, I said copy the problem times, and then I dictated the second part of the problem. So your mental energy actually goes to decomposing the function and keeping track of what you're taking derivative and what you're copying. If I am to write the original problem over here, which is x squared sine x, you can see me construct this one by just looking at what I have. So let's go and try to work this out. So I know this is y, so I say original problem times, because you see it in the answer, right, which is the y. So you always start by technically copy the problem you had, times, and this is where your logs and everything starts working, and mentally you just keep track of everything. So you only focus on one factor at a time. Every exponent will be multiplied. If it's a cube root, it's a 1/3. If it's a square, it's times 2. So what you have here is when you take 2 away, you only have x. You know it's going to be ln x. So the derivative of ln x is 1 over x, and you have times 2 because of the exponent. So 2 times 1 over x, which is 2 over x. Then you focus on the second term, because you are done with the first. You move to the next factor, and the next factor is multiplied, which means plus. That's how we know it's a plus here, because there was multiplication between these two. So now when I move to the next term, I have ln of sine. I know that sine goes in denominator. Derivative of sine is cosine goes up. Cosine over sine is cotangent. So we literally write the full answer over here. We write the full answer just by mentally decomposing the original function. Let's see it at work. Now I need you to look and listen rather than write, so that you can see the way this goes. Let's make up a function. What should I put here?
X to the 16th
X to the 16th
minus 27x
minus 27x.
divided by the
Well, you need to, how about we put this under a root or something, or a fourth root or something? Because this is just two terms, it's not
yeah,
factor.
I was going to say divided by
Divided
the
by?
cube root.
Cube root.
I don't know what else to do from there.
Well, let's put something,
E
you know.
to the sine x times 5.
E to the sine x. All right, cool.
You're real sadistic, man.
All right, that's all good. We'll take care of this. So where do we start? First off, I only have two terms here, right? So it's going to be the top minus the bottom when I start working. So the derivative dy dx is, copy the entire function as is. So that's going to be x to the 16 minus 27x divided by the cube root of e to the sine x. And now we just need to plug stuff in the parenthesis over here, and we are done. All right, so the top is going to be ln of the top, which means you will copy it as is, x to the 16 minus 27x, and you put its derivative on top. Derivative of this is 16x to the 15 minus 27, and you are done with that one, because it's always for the, if there is an ln in front of this one, right, it would be you copy the function in denominator. Remember that ln of f of x, this is the formula we're using, right? The derivative of ln of f of x is f prime over f. That's the formula. So this is my f. I copy it as is, and I put its derivative on top. That's all it is, which is why we are able to do these things mentally. It's not too much work. Now, the second term is tricky because of ease, but that's okay. You have a minus sign because this one is in denominator. Any term that is in denominator is always minus. Now, observe what I have here. I have 1/3 exponent, but I also have sine x. So technically, this is sine x over 3 as the exponent of e. Right? E to the sine x over 3. So that's what I have. Now, if I put ln in front of it, ln is going to kill e. And then I don't take the derivative of ln anymore. So that one is the oddball because of the e. But that's okay. Now I just have sine x over 3, and I need to take the derivative of that, which is cosine x over 3. And we're done. There are no calculations. I haven't done, I mean, I have to explain stuff around so you can understand the way this goes, and for the purpose of the video, which you're going to watch like 15 times. But it always goes like this. You copy the entire problem. I don't care what problem from the beginning of the chapter. Day one, right? You copy the problem here, and then you start decomposing. You have a product rule, plus. You have a quotient rule, minus. If you have a combination, every single one from the top is a plus, every single one from the bottom is a minus. Usually that's where you make mistakes. Say you have the derivative of, let's just put x squared plus 1 divided by x to the 6 cosine x. Let's say this is what you have. When you decompose this, it is going to be a plus, minus, and a minus. And then someone goes nuclear. Hold on, it's multiplication. Yeah, it's multiplication, but still in the denominator. It is 1 divided by x to the 6 and 1 divided by the cosine. So they have to be treated the same. So your terms for the parenthesis of the answer are going to be plus, minus, minus, because you have two factors that are in the denominator. If this x to the 6 is on top, then you have plus, plus, and then cosine is a minus, because it's the denominator, right? So every factor that is in the denominator gets a minus, and every factor that is in the numerator gets a plus. So if I want to mentally take this derivative very quickly, I just say, oh, I copy the problem as is, open parenthesis. Now I need to do ln of this, which is denominator is this way, and 2x, the derivative up on top. The next one is x to the 6. It's in denominator, so minus 6 over x, because 6 is the power, drops outside in front of ln. I just have ln of x. Ln of x is 1 over x, so that one. And then minus ln of cosine, so cosine goes here, and then negative sign on top. And then I can just change this into plus tangent, and we're done. So to solve, right, the problem all the way, x squared plus 1 over x to the 6 cosine x, and then we have 2x over x squared plus 1 minus 6 over x plus tangent x. Done deal. We haven't done any of the rules, right? It was copying the denominator, put its derivative on top, copying the denominator, put its derivative on top. Oh, it was to the 6, everything times 6. Copied in the denominator, put its derivative on top. Anything that was in the denominator gets a minus, anything in the numerator gets a plus. All the exponents float in front as the multiplication. Easy peasy. Yes?
So with the x to the 6th power times cosine x, even though it's ln, it will still be minus because it's
In denominator.
instead of plus because it's part of, or just minus because it's in the denominator.
Yes, because it's over, right? It's x over y. Y in denominator, it's minus ln y. So that's usually the mistake that students make. So these are the rules. And now what I want to do, just for the hell of it, just because I can, I want to write out this problem using regular rules. Turn your notebook sideways. I can generate infinite paper to the right, so all right. So don't worry about me. You turn your notebooks. So we have turning a tablet. You can generate paper. Why should we bother learning? Right? Why should we bother learning this? Well, if you don't, then good luck with the rest. It's a quotient rule. And if it's a quotient rule, you get to copy the denominator and square it. Then you copy it here, and you take the derivative of the numerator, which is 2x, minus in the quotient rule. You copy the top, which is x squared plus 1, and now you have to take the derivative of the denominator. Well, that's a product rule. So now copy the first, derivative of the second, plus copy the second, times derivative of the first. There we go. See, it fits. I don't know why I panicked. Great. Now, all you need to do is to somehow simplify this into that so that you can set it equal to 0 ready for chapter 4, okay? I mean, this is where we walk away, obviously, but I hope you get the idea, right? It's really painful to do these derivatives this way, right? Well, you can do them mentally. I mean, you can write stuff, obviously. No one is prohibiting you from writing stuff on the test. But if you learn these derivatives, imagine walking into Calc 2 next semester, and let's say, majority of the classroom did not pay attention to this, right? Didn't have need to make a big deal out of it. And then you're doing the arc length formula has the derivative in there. And as they're writing the formula, you are just dictating the derivative. Cool, huh? Boss, exactly. All right, so now, so that was the fun part. We have one more thing, and then we're done. And that is... Oh, I forgot to solve this, guys. I did say that I will do it, but I totally lied. I'm just going to leave it to you. All right.
Wait, so for that one, does the 6 get carried down to the 3?
Yes.
Oh, yes. It's that rule.
Yes. Okay. So I'll let you play with that one, and then we can do this the first thing on Thursday, right? Which you can check your answers. So when you do enough of these logarithmic differentiation, the smaller ones, right? Then do that one, and then on Thursday I can start the class working this one. We can do it on a board or something, and then you can check your answers. All right, so there is one more type of problems that we need to consider now that we are here in this logarithmic realm. And that is the derivative of, let's say, x to the x, the boss function, right? The fastest growing function for us. So you're looking at this function and you go, well, is this a polynomial like x to the square? Right? Or is this exponential like e to the x? And it's neither, right? Because if it was polynomial, you would use your nx to the n minus 1 rule. And if it was exponential, you would use the exponential rule. But it's none of those two. This is its own separate function. I call it the boss function because it's the fastest growing function that we consider in calculus. It will be back in Calc 2 with vengeance, because you will be working sequences in series with this function. Will be n to the n, and it's absolute menace over there. But now we're just going to take a friendly derivative. So function x to the x is not exponential, so you cannot use n to the x to the n minus 1, and it's not polynomial, and it's not exponential. So you can't use any of the rules you learned before. So what do? Well, you use logarithmic differentiation. Y equals, Leaf says, x to the x, and you sneak in ln on both sides. Now you see that x in the exponent, using the p rule, jumps in front the ln and creates the product rule. So this becomes ln y is equal to x times ln x. And now you get to differentiate everything following the same rules. 1 over y dy dx, because you took the derivative of y in respect to x. On the right hand side you have the product rule. Copy the first, derivative of the second, plus copy the second times derivative of the first. Dy dx is equal to y times 1 plus ln x, and we know y is x to the x, so dy dx is equal to x to the x times 1 plus ln x. So cool. So are you ready for the exam question from 3 years ago, I want to say? Find the derivative of sine raised to the 3x squared plus 1 of x. It was actually just sine to the x, so I just add some extra fluff because we can. Please rewrite this right as a sine x raised to the power. Set it to y, ln both sides, go. All right, let's take a look. Same rules, same steps, just a little bit different function. I am going to rewrite this as sine x raised to the 3x squared plus 1. So I'm just rewriting it. And when I rewrite this, I'm going to set y equal to sine x raised to the 3x squared plus 1, and then I'm going to ln both sides. Now I have the ln y equal to 3x squared plus 1 drops in front of ln of sine x, and then I differentiate both sides. I have my 1 over y dy dx, and now I have a product rule. 3x squared plus 1 times the derivative of this one is just sine x down cosine x on top, plus copy the second one, which is ln of sine x, and then derivative of the first, which is just 6x. So now we have dy dx, which is the derivative, and I have the original function y, so that's sine raised to the 3x squared plus 1 times x, and then I have this mess, which is 3x squared plus 1 times cotangent x plus 6